Welcome to this video, the 12th video in my series of videos on Georg Cantor's 1895 and 1897 articles on the theory of aggregates and transfinite numbers. Section 12 is titled Well-Ordered Aggregates, and this section starts off on page 137, where Cantor defines ordinal numbers to be the ordinal types of well-ordered aggregates, which are a particular type of simply ordered aggregate. Cantor then goes on to define exactly what is meant by well-ordered aggregate. An aggregate which is well-ordered must satisfy both of the conditions stated on page 137. Regarding the comments of page 138, the element f' which is supposed greater in rank than all of the E nu, of course may not always exist. For example, the aggregate omega, as defined on page 115, has no element f' which is greater in rank than all of the E nu. If, however, such an f' does exist, then it must satisfy the conditions that Cantor describes on this page. The symbol for a simple order on an aggregate that was introduced in section 7 is extended to a relation between partial aggregates of an aggregate. Of course, this relation only holds between certain partial aggregates, namely those where the elements of one partial aggregate are all lower in rank than a second partial aggregate. If some elements of one of the aggregates are lower in rank and some higher in rank than the elements of the other partial aggregate, then the symbol is not applicable. The extension of this symbol to apply to partial aggregates of an aggregate means that point 2 of page 120, in relation to the construction of the aggregate S from which multiplication of ordinal types is defined, could be written as shown on the screen. Of course, the order symbol has different meanings when applied to the elements of n, and when applied to the aggregates m sub n1 and m sub n2. An observation regarding the statements of Theorem A is that in some modern treatments of set theory, well-ordered sets are often defined as those sets which have a simple ordering defined on them, and where every non-empty subset, including of course the set itself, has a least element. That is, the statements of Theorem A could possibly be taken as an alternative definition of well-ordered aggregates. In the proof of Theorem A, the other case that is spoken of is the case where the lowest element f1 of f is not an element of f1. Note also that f must have a lowest rank element since f is well-ordered by assumption, and so criterion 1 of page 137 guarantees a lowest rank element. If there's any doubt about the legitimacy of the claim at the end of the proof of Theorem A that f' necessarily belongs to f1 and takes the lowest rank, then a simple contradiction argument which I'll show on the screen now suffices. The corrections for two typographical errors on page 139 are indicated on the screen. Theorem B at the bottom of page 139 is a kind of converse of Theorem A. And in the proof of Theorem B, the f1 constructed is a part of f, and so by the hypothesis of the theorem has a least element. That the least element f' of f1 must immediately follow after all of the elements of f' is, as in Theorem A, a simple contradiction argument. If f' does not immediately follow after all of the elements of f', then there must be a g, in f but not in f1, which is lower in rank than f' and which immediately follows all of the elements of f'. If g is greater in rank than all of the elements of f', then this contradicts that g is not in f1, since f1 consists of those elements of f which are greater in rank than all of the elements of f'. If there is an element e of f' which is greater in rank than g, then this contradicts that g immediately follows all elements of f'. Therefore, no such g exists. The proof of Theorem C uses transitivity of partial aggregates. The proofs of Theorem C and D are straightforward and don't really require any further explanation. The result of Theorem E will be essential for section 14. The aggregate H which is formed in a similar kind of way as the aggregate S of page 120. The main differences are that the elements G of the aggregate G are replaced with specifically well-ordered aggregates F sub G rather than just simply ordered aggregates. Also, the f sub g's are not required to be similar. We also see in the statements of Theorem E the extended meaning of the ordering symbol used which was introduced on page 139. Note that the well-ordered aggregate G may not be finite, that is, G may be a transfinite aggregate. This will be particularly useful in section 14 when it comes to sums of an infinite number of ordinal numbers. In the proof of Theorem E, the aggregate of fg's is not to be confused with the aggregate H. The aggregate of fg's is an aggregate whose elements are aggregates, thus it's an aggregate of aggregates, whereas H is effectively the union aggregate of these fg's. Since the aggregate of fg's is similar to the aggregate G, then by Theorem D of this section the aggregate of fg's is well ordered, since G is well ordered by assumption. Therefore, any part of the aggregate of FGs is well ordered by theorem C of this section. The part of H1 contained in F sub G0 is thus a part of a well-ordered aggregate, and so has a least element. A typographical error on this page is that the last H in the proof of theorem E should be H1. Thank you for watching. If you found this video useful, then please hit the like button and subscribe to my channel. You can see more videos on various topics on my channel, and if you have any suggestions for topics for future videos, then please feel free to let me know and I'll try my best to put something together. Don't forget to hit that subscribe button and keep an eye out for new videos being uploaded to my channel.